Well, good afternoon. My name is Daniela Banda Morales. Thank you for being here. I'm actually a student of sixth semester of Industrial and Systems Engineering at Tecnológico de Monterrey. Right now I'm at the InterING project. I'm developing the initiation of documentation of world-class manufacturing, specifically at Line 5 at Lennox InterING. The main reach at long term of this project is to achieve 0 defects per million of opportunities in the auto-bracing process. The actual metric is a high efficiency of 95%, but we are trying to achieve the 100%. Here we have a graph of all the leaks that we have at line 5, and as you can see, we are mainly focusing on the auto-bracer process. The objectives are to find the main causes of these leaks and the documentation of all the possible factors. We followed the MIC methodology. We only expected to achieve the define and measure phases, but thanks to all of the observation and the investigation that we did, we were able to also analyze and a little bit of implementation. First, we started with the definition phase. Here we wanted to find out the main causes of these leaks, and we did all this by the observation of the process in all of the variety of models and the shifts and the different machine parameters. And we also did a small test of samples playing with different factors. After that, we moved on to the measure phase. Here we did longer and controlled tests of each of the different factors. We did more than 70 slabs per factor. And of each of these tests, we measure the process capability of the process. This here is an example playing with the flare of the slab. And we did that for each of these factors. And after that, we moved on to the analyze phase, and we stated that the main factors come from manpower, material, and machine. And we found out that most of them come from the height of the slab, the total height, the quantity of flux in the rings that need to be braced, the insertion heat that needs to be given in each of the slabs, and the speed of the main conveyor, which leads to the auto-bracer process.
What was this one?
This one? Insertion heat.
Oh, how they hit it.
Yes, they heat it in order to seal mechanically the joint between the slab and the return bend. Okay? So we have those factors, and we did a design of experiments in Minitab. First, we started with 2 levels, but we should do it with more levels depending on each of the factors. For the height, we started with 17.4 inches and 17.63. The quantity of flux, we had 100% filled rings and some that have less at 19%. This is because if you see the boxes of the rings, you can see that not all of them are filled, so that's why we included that also. The insertion heat is a discrete variable. You have the heat or you don't have it. And the speed at 2.5 meters per minute and 2.6 meters per minute. This is all of the data that we got from Minitab, and as you can see, our p-value is lower than our significance value, which is 0.05, and that says to us that all of our factors and their interactions are way important in our process, and we should take them into account. We should solve them so we can have 0 leaks. Here we can see that the main factor is the insertion heat. It has to have it in order to don't have a leak, followed by the interaction between the height and the insertion heat and all of the other factors. And that's it. If you have any questions, yes?
It's very interesting. I don't think we've ever looked at this way. And so do we know yet what we're going to do about it? How do we improve the process as a result of our findings?
Well, actually, for example, from the height of the slab, we are now measuring. We implemented a sensor that will tell us where is the torch going to point in our slab. So in that way, we can improve the process. Of the quantity of flux, we're going to be measuring. We are going to make sure that every one of the rings is completely full, and we're trying to find a way to make it automatic and not being only measuring each of the rings because there are a lot. For the insertion heat, we are now working with training of the station before the machine, and we're also making sure that they're following a template, and after the template, it should go on, okay? And the speed of the main conveyor, We're trying to standardize it depending on the model, because sometimes the supervisors or the leaders are changing it, but we want it to be always the same. Okay? Great. Thank you.
Well done. Thank you.
Thank you.
Hello, good afternoon. My name is Armando Gomez. I'm 20 years old and I am studying industrial engineering at Tecnológico de Monterrey Campus Saltillo. Currently, I'm on my 6th semester and I'm participating in the InterING program here at Lennox International, working in the scrap reduction in lacing project. The reason that I am focusing specifically in the lacing area is because it represents the top scrap producer from plant cooling. So, in order to reduce the scrap from the area, the following actions were implemented. First of all, we have the reward to the operators from the area that generate less scrap. This takes place every 2 weeks since the 16th of April. And what we give to the operators is a diploma and a ticket that they can exchange for a special meal at the cafeteria. And in the same way as we reward, we give feedback to operators that generate more scrap in the area. Also, it takes place every 2 weeks since the 19th of April. We have here an example of an attendance list. And given the case that operators already received the feedback and in the upcoming weeks their scrap generation is not improving, then actions are taken according to the disciplinary matrix with the help from human resources. Moving on, we have the use of the aluminum plates in the segregation tables, because as we can see in the image, what happened before was that when the operators from the fin press placed the aluminum fins in the segregation tables, they used to bend because of their weight, and then they were considered scrap. And when you use the aluminum plates, we can see that this bending is eliminated. The way that this was achieved was by giving an extra set of 24 aluminum plates to each fin press, which then helped to create an operation instruction sheet that then allowed human resources to provide training to the area. And since the 20th of April, daily audits have been made in order to ensure that they are being used every day. And finally, we have the follow-up to the use of the compactor. The compactor is a tool that was already implemented in the area, but it was not used. And as we can see in the image, it helps a lot in reducing scrap in the area, because when you don't use it, the aluminum fins are loose at the end of the slab. And then this allows them to fall from the slab and be considered scrap. And when you use it, the hairpins don't allow them to fall. And the way this was achieved was with training provided by human resources according to the previously created operation instruction sheet, the definition of a maintenance plan in order to ensure that every lacing table is capable of using them daily. And in the same way as with the aluminum plates, we have daily audits since the 5th of May. And for the next steps, we have the tests for the use of individual aluminum plates that will help us in the future eliminate the segregation tables and reduce material management that causes aluminum fins to get damaged. Moving on, we have the implementation of the reward and feedback incentives, but for the fin press area. This to keep reducing the scrap in the area. And finally, we have the proposal of relocate the compactors, because where they're placed right now in the segregation tables allows them to fall to the ground and get damaged. And now that we talk about the actions, we are going to talk about the results. In the top graphs, we have the scrap from the lacing process, in which the month of May, in which all actions were implemented, represented a 43% respect the month of March. That was when my project started. Moving on, we have the scrap from coil shop, in which we have a 39% reduction. And finally, we can see the Pareto scrap from coil shop, in which we can appreciate that although the lacing process still represents the top scrap producing area, in the month of March, the difference respect the second place was from more than $6,000. And in the month of May, the difference was just from above $1,000. And that would be everything for me. Thank you for your attention, and if you have some questions, I will be happy to answer them.
The aluminum plates, did we have them before and we just weren't using them?
Yes, they were only used in the fin presses, and when they were taken to the aluminum fins were taken to the segregation tables, they were taken back to the fin presses, and when you lift them, you can see that it reduces the scrap. instantly.
Very well done.
Thank you.
Nice job.
Thank you.
Hi, good morning, everyone. My name is Julian Adan. I'm 21 years old, and I'm in sixth semester of industrial engineering. Right now, I'm in the intern program of the Tecnológico de Monterrey, Campus Saltillo. And during this program, my project is about the SMED methodology implementation here in Lennox Schooling in the expanders area. Well, to start talking about my project, we need to say that besides this methodology implementation, one of the objectives of this is to achieve a reduction of at least 10% in the total setup chain time in the different expanders. So we are going to see here now in the next slide, we have a table in which we have the different models of the expander. They are divided in 4 different groups. Each group because of the characteristics and the different parts of each of the expanders. Each of the expanders has the baseline, that it was the time that it take for do the setup when I arrived here to the company, and the goal with the 10% reduction that we were talking before. If we go to the example for the expanders 2, 3, 4, and 5 of aluminum, we can see that our baseline was of 44 minutes. With the reduction of the 10%, the goal was to reduce it to 38 minutes. And with the actual improvements of the project, we can see how we reduce it to 25 minutes, which represent a reduction of 41%. Now we're going to see how we achieve these reductions. Well, first of all, we need to say that in the graph on the left part of the screen, we can see how it was done before the SMED methodology implementation. In this graph, all the necessary steps for doing the setup change, all the activities were done by only one person. It was a technician in this case, and he realized all the activities in a sequential way. So we can see here in the below part of the graph all the different activities necessary for the setup change. These activities in the right part of the name have a letter E or a letter I. What this represents is if the activity is external or internal. The external activities are the ones that we can complete with the machine still working. But for the internals, we need to have the machine stop in order to successfully complete them. And as we can see now in the right part of the screen, in the after SMED methodology implementation, we can see that the technician is still working in the setup change, but added to the technician, we have both expander operators in order to change from sequential activities to simultaneous activities. So we also have the external activities taken out of the pacemaker, in this case the technician, because right now the activities are done with the machine still working, so it doesn't count in the time that the machine is stopped. And well, to see how we achieve this change, we are going to see the improvements that we did during this project. First of all, we are going to talk about the infrastructure. We redesigned the stacks, the racks of each of the expanders. In the case of the expanders 1A and 1B, there is the one over there. We are building one right now because it didn't count with one. And we are working in standardizing in the other expanders. We can see also the training with the help of Human Resources Department. We do a training to all the expander operators and the call trainers in order to achieve what we were saying in the slide before about the simultaneous activities. And for doing that, what we also do was standardizing work by creating and updating the operation instruction sheet that we have in each of the expanders. Also, with all these improvements, what we can see here is the production improvement of the project. We can see that this project, with all the reduction in time, it produced an improvement of approximately 500 hours of available time in the expanders area, which represent a total of 12,275 extra coils. And well, for the next steps, what we are doing right now, we are with the follow-up of the project by doing all the controls and the standardizing of each of the improvements. And well, that's all. If you have any question, please feel free to ask.
As part of the follow-up, do we have a process by which you're going to measure every time we do a changeover? Do we capture that and measure it? Track it?
Right now, what we are working with the help of the supervisor and the leaders, is with the with audit all the changes that they are done right now. But one of the next steps could be to measure all the time, to just to be sure to have a control and to be sure that the project is still working.